Good morning, everyone. My name is Adish Meduri, and I'm from Mechanical Department. Yeah. Good morning, everyone. My name is Adish Meduri, and I'm from Mechanical Department. So today's uh, concept video subject subject is design of machine elements, and the topic for today's concept video is brake fail in heavy vehicles. Functions of first to understand brake fails, we need to understand functions of brakes in design theory. Brakes are designed to convert kinetic energy from vehicle motion into thermal energy via friction, absorb and dissipate this energy without failure or loss of performance. This makes heat generation, wear resistance, and torque capacity the core design aspects. As you can see, the brake caliper assembly here, and the brake pads of it, and the brake rotor. We also see the wheel bolt and wheel bearings. So to understand how a brake fails, we need to understand how brakes are designed, right? So this is the design. So to understand design, first we need to understand what brakes are. Brakes are nothing but which converts kinetic energy, that is vehicle's motion, into thermal energy via friction. Absorb and dissipate this energy without failure or loss of performance is called brake. This makes heat generation, wear resistant and torque the capacity, the core design aspects. Types of brakes in heavy vehicles. Heavy vehicles typically use drum brakes, common in trucks and buses. Disc brakes in newer models or for front wheels, disc brakes are used. Air brake system, pneumatic actuation, retarders, non-friction supplementary brake. So these are the four main types of brakes. This is the drum brake, as you can see. As you can see, this is the drum brake. This is the disc brake. This is the ABS brake, air brake system, and this is the retarders. So in the drum brake, it's commonly used for truck or buses. And a disc brake is a newer model for front wheels of a vehicle. Air brake system is nothing but a pneumatic actuation. Retarders are non-friction supplementary brakes. So to understand thermal energy calculation, we need to understand this. When a heavy vehicle brakes, the kinetic energy of the vehicle is converted into heat, right? So in the first slide, I've told you uh, brakes are nothing but conversion of kinetic energy into thermal energy. So this is the equation of kinetic energy to thermal energy. Q equals to half mv square, where Q is heat energy to be dissipated. M is the mass of the vehicle. V is the initial velocity. Q equals to half mv square. Design relevance. This energy must be absorbed by the brake pads, disc, drum, and surrounding structure without exceeding thermal limits. Every brake has a thermal limit. For example, a 20,000 kg truck moving at 25 meter per second, that is 90 kilometer per hour, must dissipate. The, how much should it dissipate? So 90 kilometer per hour is given, and mass of the vehicle is given. Then we need to do Q equals to half mv square. Q equals to half m equals to 20,000 into v, which is 25 meter per second. That is 5 square. Mv square equals to this. Okay, so everyone, I guess, understood this. So the next topic is common design related causes of brakes. Common design related causes of brakes is there are four types: thermal failure, lining wear and degradation, improper material selection, and air system failures. So thermal failure. In thermal failure, you can see the disc brake dissipates more heat than it requires, which is a thermal failure. In lining and wear degradation, you can see that the brake pads are wearing out and the metallic structure is degrading. In improper material selections, you can see that the casing tube with actuator top removed, its casing showed localized corrosion at the diaphragm level indicator area. So, with the wrong material selections, there can be rusting or corrosion taking place. Air system failures. So, thermal failure, the main culprit mechanism. Brakes convert kinetic energy into heat. I've said that Q equals to half mv square. If heat is not dissipated, brake fade occurs. Friction reduces. Cracking, wrapping of drum disc, loss braking, torque. Design solution for this: high thermal conductivity materials. Example, cast iron should be used, or ventilated discs or cooling fins. Thermal stress analysis need to be equals to EA delta T. It's an equation, as you can see. So these are the design solutions. So I'll just repeat it once again. Brake convert kinetic energy into heat. If heat is not dissipated, brake fade occurs. Friction reduces, cracking, wrapping of drum disc, loss of braking of torque. So design solutions are high thermal conductivity materials like cast iron, ventilated discs or cooling fins, or thermal stress analysis should be E equals to EA delta D. Brake lining wear issues. The issues here is continuous braking leads to friction material loss, right? Uneven or excessive wear reduces friction and torque. Brake plate flexing can cause uneven contact pressure. So the design consideration for this is use wear resistant materials, maintain uniform contact area, include wear sensors in the design. So you can see that the brake drum and brake lining here, where wearing of the edge brake drum and wearing of the edge brake lining is taking place. So you can see this, right? Yeah. So this is the worn out one. This is a broken one. Material selection, why it matters. So material failure modes. Thermal fatigue. Thermal fatigue may be one issue. Creep at high temperatures or crack initiation due to repeated loads. These are the reasons that material degradation takes place. And design approach for this is use materials with high fatigue strength, thermal resistance, apply SN curve analysis and fatigue criteria. Goodman or Soderbergh's methods need to be used. Pneumatic system failures, air brake, design failure points, leak in airlines or reservoirs, delay in actuation due to pressure loss, compressor underperformance, design safeguards, redundant airlines, emergency spring brakes, pressure monitoring and regulation design. So the design failure points are nothing but leaks in airlines or reservoirs, delay in actuation due to pressure loss, compressor underperformance, design failures. These are the three main design failure points. And to safeguard this, the design safeguards are redundant airlines, emergency spring brakes, pressure monitoring and regulation designs. So here we can see what air brake system is, right? Hmm. So this is the front brake, this is a delivery line, and this is a delivery line. This is a foot valve, and this is a discharge line. This is a compressor. Compressor goes through governor goes to reservoir goes to supply line, and it goes here, braking system, and then the back brakes, that's rear brake, also applies the same thing, delivery line, using delivery line. So same, front, exhaust air, reservoir, rear, right? You can see the brake being applied and you can see the brake being loose. Parts and working advantages. This is the brake drum. This is the axle shift shaft. This is a return spring, as you can see, and this is a cam roller. This roller here is known as cam roller. This is a brake shoe lining. This is a lining of the brake system, and this is adjusting done to the axle. This is slack adjuster, and this is the brake drum. Real world examples. Case 1. Runaway truck on downhill road. Causes brake fade due to overheating, thermal design neglected. Case 2. Bus accident from disc crack. Repeated thermal stress. No fatigue resistance design used. Lesson all were avoided with better mechanical designs. Design recommendation. Select material for thermal and fatigue strength. Use ventilated components and cooling designs. Ensure proper thickness contact pressure, and geometry. Incorporate fail-safe braking in air brake systems. Design for worst-case load and braking scenarios. As you can see, hardware and springs. This is a wheel cylinder. This is a backing plate, and this is a brake shoes. This is a self-adjuster, and this is a parking brake cable. So, for conclusion, brake failures are often designed related, not just maintenance. Application of design of machine elements can prevent failures. A multidisciplinary approach, that's thermal fatigue and stress, is essential. Safety begins at the design table. Thank you.